Okay, thank you. Good morning. Sorry for not being there. Today I will talk about a new bound on the rank of tensor products of W states, and this is based on a joint work with Alex Casarotti and Pierpaolo Santarsiero, which should be there on the contrary of me. So let's start to see what we mean by tensor rank and so on. We will focus on partially symmetric tensors. So we consider V a C-vector space of finite dimension, and then a partially symmetric tensor is just an element of this tensor product of symmetric tensors. So T is in sim D1V tensor sim DKV. Okay. Now, if we fix a basis E1 En of V, then the symmetric algebra of V is isomorphic to the polynomial ring in the unknowns E1, En. And so we can think to T just as a tensor product of homogeneous polynomials of degree D1, D2 up to dk. Okay? Now, there are some special partially symmetric tensors, which are the building blocks of all the others, which we call elementary partially symmetric tensors. And they are of this form. So they are the tensor product of powers of linear forms. Okay? So they are of type L1 to D1, tensors, LK to DK, where these LIs are linear forms. And since these are building blocks, every partially symmetric tensor can be written as sum of these elementary partially symmetric tensors, and the minimum number which we need to write our partially symmetric tensor T as sum of elementary partially symmetric tensors is called the partially symmetric rank of T, and is denoted with this rank D, where D is the multi-degree of our tensor. Now, we introduce the other main character of the talk, which are W states. So we fix V equal to C2, and the W state of order D is just this symmetric tensor, WD, which is E0 to the D minus 1 times E1. So this is a symmetric tensor. The W states are very interesting tensors for many reasons. For instance, they appear often in quantum information theory, complexity theory, and also in the same tensor theory because they give interesting counterexamples, for instance, to the multiplicativity of tensor rank and so on. I'm probably not the best person to.
One second, Stefano. We're having some technical issues.
Okay.
Maybe is it open in the browser? Maybe.
No. It's gone.
It's very weird. Because the window doesn't exist anymore. Maybe it's no, it's not the second. Yeah, maybe that one. Yes. Are there more windows? No, right? Open
It seems so.
But the voice was still there, right? So the windows it is
You can see on the other. Ah, it's crashed. Okay. Yes. Yes.
So Stefano, we're trying to connect again from the meeting room.
Okay. Uh-huh.
Maybe we leave the size like this. We leave it like this, right? Okay, you can resume. I'm sorry.
Okay, okay. These W states are very important tensors for the reason that I told you, and they appear many times also in physics. Even though I'm not the best person in the audience to explain you the reason, I just know some parts that they are very important, but probably there are more persons which are more experts than me to explain you the real reasons. But what is important for our talk is that also the tensor product of W states is an interesting type of partially symmetric tensor, which is just the tensor product of W states of different degrees. They could also be the same, but it's just WD1 tensor WDK. And since they are important, it makes sense to try to understand how complex they are, and so to compute their partially symmetric rank. So, to help us to compute this rank, we can use a geometric perspective on the tensor rank, which is given by the Segre-Veronese varieties. So we consider the multi-projective space given by key copies of P1 with these coordinates x10, x11 up to xk0, xk1. And we think to each P1 as the projective space of the degree 1 of the linear forms in the unknowns ei0, ei1. Okay? Once we fix the multi-degree D, we can define the Segre-Veronese embedding, which essentially take the linear forms L1, L2, Lk, and send them in the elementary partially symmetric tensor L1 to the D1, Lk to the Dk. And the image is the Segre-Veronese embedding with the multi-degree D. So since the points of the Segre-Veronese variety, which is the image of this embedding, are the elementary partially symmetric tensors, then computing the partially symmetric rank of T amounts to find the minimum R such that T is in the span of R points which lies on the Segre-Veronese variety. So we need another geometric object for our study, which is given by two hypercubes. So these are special type of zero-dimensional schemes, which are defined as follow. We take Z in P1, which is the length 2 zero-dimensional scheme supported at the point 0, 1, and then we denote by Zk the product of Z key times, okay? So this will be a zero-dimensional scheme in the multi-projective space. And why this is important? Because we have this lemma proven in a paper by Ballico, Bernardi, Cristandel, and Desmundo in 19, which essentially says that if we fix our multi-degree D, then the tensor product of our W state is a tensor which is in the span of the embedding of our two hypercubes via the Segre-Veronese embedding, okay? So we take ZK, we embed, we take the span, and there we find our partially symmetric tensor. Now, we want to use this geometric interpretation to find a bound on the partially symmetric rank. We use a technique which was introduced in the same paper and which allowed to prove this theorem. So, if we have WD1 tensor tensor WDK, in the same paper, it is proven that the partially symmetric rank is at most 2 to the k minus 1 times the sum of the degrees. What is the idea of the technique used for this theorem? We take L1, LA curves in the multi-projective space such that ZK is included in the union of these curves. And so we have that the tensor product of our W states is in the span of the embedding of ZK, and this is trivially in the span of the union of the embedding of our curves. Okay, so this means that the tensor product of our of our W states can be written as sum of tensors Ti, which are in the span of the embedding of these curves. And so this is a decomposition, and thus we find that the partially symmetric rank is at most the sum of the partially symmetric ranks of these Ti. So the question is how to choose these curves Li. And an answer is given by rational normal curves. Indeed, suppose that we have Li in the multi-projective space, a smooth curve of multi-degree h1, hk, where the hi's can be just 0 or 1. Then, if we embed Li with the Segre-Veronese embedding, we get a rational normal curve of degree f, which is h1 d1 plus hk dk, and thus the span of the embedding of, the span of this rational normal curve is a pf in the PND, okay? A classical result, but is easy to see, states that any point T in this PF is the span of is in the span of at most f points on the rational normal curve. Okay, but this rational normal curve lies on the Segre-Veronese variety. So these points are also points of the Segre-Veronese variety, and thus the partially symmetric rank of T is bounded by f. Okay, so if now all the curves L1, LA are as above, then if we call Fi the degree of the rational normal curve given by Li, the partially symmetric rank of WD1 tensor tensor WDK is smaller or equal than the sum of these degrees Fa. Okay? What is done in the paper by Ballico and others is to use the 2 to the k curves of P1 with all the possible multi-degrees h1, hk as hi varies in 0, 1, and then they conclude by using the previous inequality. To get our new bound, what we do is to do a different choice of the curves, and then to compute explicitly the Ti whose sum is the tensor product of W state. We don't say just that they exist, but we compute explicitly, and then we apply the Sylvester algorithm, which is a classical algorithm for binary forms to minimize this sum. Now I will be more precise. So let's start with the choice of the curves. Recall that we have our multi-homogeneous coordinates in the multi-projective space, and then we fix our multi-degree D, and for any j subset of the set of natural numbers from 2 to k, we define Lj, the 1, 1, 1 curve in the multi-projective space defined by this ideal ij. Okay, it's not really important who this ideal is. Now I will show you a picture to understand more or less what is the situation. What is important to keep in mind is the presence of these epsilon rj, which are defined to be 1 if r belongs to j and -1 otherwise. if we embed Lj with the Segre-Veronese embedding, we find CdJ, which is a rational normal curve of degree d1 plus d2 plus dk. And I will not explain you in all the details what happens with these epsilon ij's, but what we have to keep in mind is that they are the core of all the combinatoric behind the problem, which allow us to simplify a lot of the computations, okay? So just to see a picture, this is the choice of our LJs for k equal 3. So we are the 4 bisector in some sense of passing through the origin, okay? Now, what we do after we define the curves is to compute explicit parametric equations for the linear space given by the span of these rational normal curves. And this is done again in terms of the combinatoric of the epsilon ij's. After that, we know that the tensor product of our W state is sum of Tj, of these Tj's, where Tj is in the span of Cjd, okay? And this is a linear system. What we do is to find many explicit solution of this linear system, not all, but enough for our purposes. And in a minute, it will be clearer what mean enough for our purposes. But just to see an example, for W3 tensor W3, we can prove this equality, okay? Where T is in the span of C33 and T2 is in the span of the other rational normal curve in this case, and they are defined in these two lines. As you can see, there are many symmetries between them, and if you sum, you get 9 W3 times W3, okay? Now, the next step is to apply the Sylvester algorithm. We said the Sylvester algorithm allows to compute the rank of a binary form, but for the moment we have partially symmetric tensors, not binary forms. But what is the point? We denote by VDJ the vector subspace of this tensor product, the tensor product of symmetric powers, such that the projectivization of VDJ is the span of our rational normal curve CDJ, okay? Since CDJ is a rational normal curve, VDJ is isomorphic to the vector space of binary forms of degree D, okay? And we can give an explicit isomorphism exactly between VDJ and the degree D binary forms, again in terms of combinatorics of the epsilon ij's, and we call this isomorphism Phi. This isomorphism send the points of the curve to power of linear forms. And so the rank of Tj with respect to this curve equals exactly the rank of the binary forms Phi of Tj, okay? For instance, if we apply Phi to the previous example, we find Phi of T, which is this binary form, and Phi2 of T2, which is this other binary form, okay? Now, since we have binary forms, we can apply the Sylvester algorithm, and this is a little bit technical, but what we can prove? We take Tj, as J varies in the usual set, a solution of our linear system, okay? What we can prove is that as the solution varies if you take any solution of the linear system and you take any Tj in this solution, then the rank of Phi of Tj is at least the 1 plus dk minus 2k plus 2. Okay, so this is the minimum. And we can give explicit solutions of this linear system such that the rank is the minimum for all the Tj of this solution. Okay, so putting all together, we can prove this theorem that this is the rank, the tensor rank for those who knows, but what is interesting for this talk is this part. That is, the partially symmetric rank of the tensor product of W state is at most 2 to the k minus 1 times d minus 2k plus 2. And so this improved the previous bound by 2k times k minus 1, okay? Now we can compare with previous result the differences in our strategy. And first of all, we have a smaller number of curves because we have 2 to the k minus 1 instead of 2 to the k, but we pay a price for that because all our curves are of multi-degree 1, 1, 1. So since this degree is higher, the general rank of the tensor in the span of these curves is higher. However, the second difference balance this part. Indeed, we compute explicitly the TJ, which gives our whose sum is the tensor product of W states. And luckily, these TJ do not have general rank with respect to the curve, but a lower rank. Okay, so computing explicitly these TJs allow us to give the better bound. Now, I want to conclude in the last minutes by showing you an explicit and effective algorithm to compute an explicit decomposition of WD1 tensor WDK with the length given by the bound of our theorem. Okay. The fact is that we can choose a very easy solution of our linear system such that for any Tj in this solution, Phi of Tj can be just one of these two binary forms, okay? The first if the cardinality of J is even, and the second otherwise. Now, since we have just two binary forms, we have to apply the Sylvester algorithm to just to these two binary forms, not to the k minus 1, okay? And then we can apply the inverse isomorphism of phi j to compute all the addenda of our decomposition, just using the combinatoric of the epsilon ij. But this is very easy and very effective for a computer because it's just a matter of substitutions. There are no computations to do. The only computations are for decomposing these two binary forms with Sylvester algorithm, okay? So what is explicitly our algorithm? We take in input the integers k and then the 1 dk, and as output we give a decomposition of WD1 tensor WDK of the prescribed length. The procedure is, first of all, we have to do some choices to fix the combinatoric of the problem. This is a little bit technical, but it is a very easy step to be done. It's just a choice, okay? It's not really important. Then we set F and G, the two binary forms defined in the previous slide, so the two possibilities for phi j of Tj. Then we apply the Sylvester algorithm to F and G, and we compute the minimal decompositions AF for F and AG for G. And finally, we apply phi j to the minus 1 to AF if the cardinality of J is even, and to AG if the cardinality of J is odd. And then we return the sum of all these preimages, okay? And this will be our decomposition. And to conclude, I want to show you this conjecture, which essentially say that for the case of two factors, WD1, WD2, our bound is sharp. That is, the partially symmetric rank is 2 times D1 plus D2 minus 2. We know that the conjecture is true for W3 times W3, because in a paper by Christandel, Jensen, and Zuidam, it is proven that the partially symmetric rank is 8, which is the bound we give, and also for W4 times W4, in a PDF, which is published just on the personal website of Matsuei Gawaska. It is proven that the partially symmetric rank in this case is 12, which is exactly what is predicted by our bound. So we suspect that the bound should be sharp, at least, and probably just for the case of two factors. So I think that I told you everything I want to, and I thank you for your attention.
Okay. So some questions? So if not, then let's thank the speaker again.
Thank you.
Grazie Stefano.
Grazie, bye bye.